In this video, we address the provision of the inertial response that is a determinant factor for the stability of microgrids. We address the following three learning objectives. Firstly, what is the inertial response level of microgrids during the grid-connected and islanded modes? Secondly, which components are able to emulate the inertial behavior? Thirdly, how the inertial emulation loop is implemented in current source and voltage source-based units. Here we remind the swing equation for the rotating mass of the electrical machines with the angular speed omega. The input mechanical power, which can be supplied by a prime mover, is converted to the output electrical power. If the mechanical power is equal to the electrical power, then the rotating speed remains unchanged. However, if there is an imbalance between the mechanical and electrical power, then the rotating speed of the mass starts to change. As it is shown in the equation, the rate of change of the rotating speed depends on the value of h, or the so-called inertia. In other words, the level of the inertia determines the rate of change of the frequency of electrical grids. If the inertia has a low value, that is often the case for microgrids, then the grid is more vulnerable to the disturbances. On the one hand, if a microgrid is connected to an external grid, the so-called grid-connected mode, then the frequency and voltage are dominantly controlled by the grid. If the grid is strong, then it provides high levels of inertia. As a result, the rate of change of the frequency following a contingency event has a very low value during the grid-connected mode. On the other hand, if the microgrids are disconnected from the external grid, the so-called islanded mode, then typically it has a low level of inertia. This is due to the fact that most of the DG units connected to the microgrid through the power converters typically do not provide any inertial response. The rotating mass-based generating units, which are directly connected to an electrical grid, do inherently provide the inertial response. On the one hand, if the frequency of the network increases, then a certain amount of energy is stored as the kinetic energy in the rotating mass. On the other hand, if the frequency of the network decreases, then these units release their kinetic energy back to the network. Various types of DGs, like reciprocating engines as well as the gas turbines, inherently provide the inertial response. On top of this, a number of energy storage technologies, like the prime hydro energy unit and the compressed air energy storage, support the inherent inertial response. Unlike rotating mass-based generating units, power electronically interface units do not have any rotating mass, which is directly connected to the grid. As a result, these units do not typically procure any inertial response. Nevertheless, since power electronic interface units have full control over the power, they are able to emulate the inertial behavior of the rotating mass. To achieve this, an additional inertial emulation loop shall be implemented in the active power frequency control loop of these units. Various types of DGs, like photovoltaic solar units, as well as the wind generators, can be enhanced by the inertia emulation loop. A number of energy storage technologies, like flywheels, already release the kinetic energy stored in their rotating mass using the power converters. Moreover, battery energy storage technologies are able to emulate the inertial response either as current source or voltage source types. The implementation of the inertial emulation of the power electronically interface units mainly depends on the type of the interface. If the unit has the current source-based type, then it is able to adjust the active power output delta P according to the input frequency variations delta omega. Taking into account the swing equation, the inertia emulation loop can be implemented as it is shown in the figure. The parameter h mu can be set in such a way that a certain level of the inertial response is provided by the current source-based units. Current source-based units, like photovoltaic solar and wind generators, are able to employ this loop to increase the inertial response of the microgrids. Voltage source-based units become able to emulate the inertial response using the swing equation. In these units, typically the value of the frequency is dominantly set by the units. The swing equation is implemented through an integrator for the input active power variations in such a way that the output frequency variations are suppressed by the value of h mu. Energy storage technologies like lithium-ion batteries and flow batteries are two good examples of voltage source-based units which are able to emulate the inertial response. It is worth mentioning that there is a clear trade-off for the value of h mu between the performance response and the stability of microgrids. On the one hand, low values of h mu might not satisfactorily emulate the required inertial response, and the overall microgrid stability might be put at risk. On the other hand, if the h mu is set at high values, then the frequency response of the microgrid might become very slow. In this video, we first address the inertial response in microgrids during grid-connected and islanded modes. While the strong grid provides a very high level of inertia, the islanded microgrids have typically very low levels of inertia. To increase the inertial response of the microgrids, we show how the inertial emulation loop can be implemented in both current source and voltage source-based units using the swing equation.